Welcome everybody for the brewing session on pasteurization for low and non-alcoholic beers. It's my privilege to introduce Alek Egi from Kwantlen KPU Brewing and Brewing Operations School. I had the pleasure of working really for, I guess you were the boss, weren't you? I guess so. Working for Alek for 7 years in the program. I co-instructed with Nancy Moore, and so I got to see firsthand his expertise. He has a background in engineering and believes in demonstrating the importance of paying close attention to every detail when it comes to brewing beer. He's passionate about sharing his knowledge with the students and making sure that they develop an understanding of every single step of the brewing process and how each step can affect the finished product. Alek is most interested in the science of craft beer because of the capacity for inventiveness and creativity, but he also enjoys the challenge of meeting and the increasingly high standards of the industry. Originally from Europe, which you'll hear when he speaks, Alek is familiar with the older and more traditional styles of malting in the brewing industry. He moved to Canada and worked at Canadian Malting Barley Technical Centre in Winnipeg before moving to BC. He believes in combining his knowledge of traditional European brewing concepts and years of professional experience in the Canadian beer industry. It has given him a unique perspective when it comes to observing new trends in brewing. So welcome, Alek. Thanks for doing this.
Oh. Thank you, Ken. Thanks for having me here and for the opportunity to talk about pasteurization. It seems that, lately over the last year or year and a half, every single brewing conference, there are sessions on pasteurization or workshops or pasteurization and non-alcohol beer and so on. So I'm glad I have a chance to talk about this here. Obviously, I also teach KPU students about pasteurization. We spent 3 weeks talking about it. We just finished talking about pasteurization, so after one of those classes, the student came and asked me, well, what are you going to talk about at the conference? And then I guess what they wanted to find out is if I was going to ask you to do some calculations when it comes to pasteurization, right? So you can relax. I'm not going to ask you to do any calculations. To earn the right to suffer through those calculations, you really have to be a KPU Brewing student. So I'm sorry, I apologize ahead of the time, right? So, okay, so as Ken said, I'm going to talk about pasteurization, and then we're going to, of course, talk about non-alcohol or low-alcohol beer. So really, the objective of this talk is that I really want to put emphasis on the science behind pasteurization. So I want to make sure that people have good understanding. What are we actually talking about when we're saying we're pasteurizing beer to so many pasteurizing units, right? And then we're going to focus on low alcohol, non-alcohol beer, and so on. So for us that we've been working in the brewing industry, the general assumption is that beer is a very safe food product, if you want to call it a food product, because there's no pathogens that can grow in beer, right? And we all know what the main reasons for that for those are, right? First of all, typically we have alcohol, ethanol, 4% or higher. So obviously a lot of microorganisms cannot grow in the presence of ethanol. Ethanol becomes toxic for the yeast even, right, at a certain point. Then there's the hop compounds, the antimicrobial hop compounds. The product is relatively low in pH, so that's another obstacle. And then, of course, anaerobic environment, CO2, pressure, and finally, there's not a lot of residual extract in beer, right? So if you look there at the bottom, oops, sorry, go back, wrong button, here. So this is what we, in food industry or beverage industry, we call hurdle technology, right? So those are different obstacles or hurdles that are, antimicrobial or bacteria killing or bacteria inhibiting factors. And those factors, where you have a few of them, when they put, if they work, at the same time, sort of synergetically, they're going to prevent a lot of different microorganisms, from growing in that environment. taken individually, some of these hurdles, are going to stop some microorganisms from growth, but if you put them all together, they're there in order to make that food product or a beverage safe for consumption and also palatable during the, stated shelf life of a product, right? So those are the main hurdles if we're talking about traditional beer, right? Beer that has alcohol. Even in, traditional beer, obviously some microorganisms can grow there, but again, luckily for us, these are not pathogenic microorganisms, right? So when we talk about beer spoilage microorganisms, so those are the things that can, affect the flavor and the appearance of the beer, but they're not that dangerous for us, right? So we have different brewing yeast, wild yeast, variety of bacteria. And, I've listed some of the most common ones, which we all know probably, like gram-positive lactic acid bacteria, gram-negative. Then we have different yeast strains, some of which can actually ferment fully fermented beer. When we say fully fermented, we talk about regular brewing yeast, right? Also, when it comes to the contamination level, right, that's very different from one plant to another, as well as the types of microorganisms that, might be common for one brewery, but not so common for the other brewery. Also some things to keep in mind. So when we change the environment, in which microorganisms can grow, so now if we're talking about low alcohol environment or no alcohol, those beers do lack some of those hurdles that we've seen in the first slide. So obviously alcohol is the big one, but also some other things might be very different, right? With no alcohol or low alcohol beer, lots of those products have actually lower, hopping levels, so less IBUs if you want. They might have higher sugar levels depending on, which technology are you using to produce the beer. Might have actually higher pH levels, right? So all of those things, again, put together means that now there's a whole range of different microorganisms that typically do not grow in traditional beer, but, you can find in non-alcohol beer. I'm not going to go through this whole list, but there's like lots of different bacteria, different yeast, and so on. And also, the research shows that even things like E. coli or salmonella can actually survive in non-alcohol beer for up to 2 months. So now all of a sudden, we do need to worry about food pathogens, right? If we're, considering, non-alcohol or low alcohol beer. So, as we know, this is the segment of the market which is growing, right? So it's growing in North America, it's been growing in Europe for a long time, other parts of the world. And there's many different reasons for, growth, like, social regulations, consumers' health awareness, religion, responsible drinking and driving, changing demographics, all those different things, right? So now that, like more and more brewers and lots of craft brewers are considering, making maybe or introducing those types of products into their portfolio, we really need to, think about shelf life stability, but more importantly, really the safety of the consumers when we're, talking about those products. Now, with non-alcohol and low-alcohol beer, there's also different production methods and different preservation methods. So I'm just quickly going to show you some of those just for a reference. It's really not the focus of this presentation. But just when we compare this to traditional beer, these are kind of our options with non-alcohol beer. Generally speaking, you have physical methods and biological methods. Physical methods are largely actually de-alcoholization, right? So you have options of thermal processing like boiling and vacuum distillation. But it's mostly in the industry what's being used is really the membrane or cross-flow filtration, really the reverse osmosis. When it comes to biological methods, right, so we have no fermentation. We actually do not ferment wort at all. We're just diluting it, stripping it with CO2, adding carbonation, acidification, some maybe flavors. And then there's the changed mashing procedures. And then after that, we can use some limited fermentation or special yeast. So when we say special yeast, it's, maltose negative yeast. So I'm going to tell you towards the end of the presentation what we've been doing at KPU, but, we've been using actually those biological methods with change mashing and maltose negative yeast. Okay, so then the preservation methods, right? So we have an option of sterile filtration. There's different preservatives that you can use, sorbate, benzoates. There's now some natural antimicrobials which are produced from different funguses, like citizen fibers and so on. And then there's the pasteurization, right? So when it comes to pasteurization, the options are, for very small production, like we at KPU, small batches, we can do batch pasteurization. But most of the time, in the industry, it's tunnel or flash pasteurization. So that's where the focus is going to be, like on pasteurization. Okay. Again, if we look at the hurdles here at the bottom, right, we've removed the alcohol, or mostly removed the alcohol, but now in order to make the product safe, we're going to do pasteurization. So a certain number of pasteurizing units would be required in order to, make non-alcohol beer safe for production or consumption. All right, so again, in order for us to actually know exactly what we're talking about, we do need to mention some of the theory behind pasteurization, right? So it's been around for a long time, right? It's been developed like over 150 years ago by Louis Pasteur, and it really involves the reduction of microorganisms by heating. People have been actually using heat to preserve food for a long time, right? There's records of people doing that in Asia for like hundreds and hundreds of years ago, but the theory really was developed by Louis Pasteur. So the objective is to, after we introduce some heat treatment to the product, that we have actually a minimal effect on physical or colloidal stability of the product and also a flavor stability. And we want to combine that with really the maximum biological stability of the product, right? So again, we can say that pasteurization is relatively mild heat treatment, which really reduces the number of microorganisms. So that's different from sterilization, right? Which is, if we're talking about, target temperatures in sterilization, we're typically like 100 degrees Celsius or higher, right? In pasteurization, mostly people talk about 60 degrees Celsius, but it doesn't have to be 60, right? We'll talk about that. So then, one of the main decisions that we need to make is what is the level of treatment which is required in order to, have the product which is going to be stable, right? We can talk about some of the specifications, right? So what the pasteurization does, it really achieves this, statistical kill rate of specific microorganisms which might be present in the product with the heat treatment, right? So this is defined by a formula, and we're going to take a look at the formula. Again, we're not really going to do any calculations, but it's important to understand how this whole theory and formula and everything else works, right? So what are the most important factors? What are the critical factors, right? So first of all, obviously, we have the, the combination of the temperature and time, right? So when we're talking about pasteurization units, you'll hear that, one pasteurization unit is 1 minute at 60 degrees Celsius, right? Okay. So obviously, a combination of those two. But then there's other things that are also important, which might not be in the formula, right? Like the type, but also the physical state of any present microorganisms. Then there's the question, well, what is the concentration of microorganisms? How many contaminants do we have? And then also the composition of the product, right? Again, we've talked about these different hurdles that are here, right? So, okay, so if we don't have alcohol or have very low alcohol, less than 0.5% by volume, right? So what's the pH? What are the IBUs? What are the carbohydrates that are present there? The carbonation level and so on. So those are the important things to keep in mind. Okay, so we're going to start with talking about these two different values, right? So again, the level of pasteurization which is required in any product really depends on the resistance to heat of the microorganisms that might be present there, right, or on their thermotolerance. So again, the pasteurization units are really the measure of the intensity of that heat, which is applied during the heat treatment, which we're giving to the product, right? So in order for us to understand the pasteurization unit formula, we need to talk about these two values, right? The first one is called the D value, or the decimal reduction time. And the second one is the Z value, or it's the thermal resistant constant, right? So we're going to look at those and see what they really are, right? So starting with the D value, or decimal reduction time. So this is really the time which is needed at a given temperature. We might say 60 degrees Celsius, but it doesn't have to be 60 degrees Celsius. It can be 55 or 58 or 62 or 68 or so on, right? So again, a time at any temperature which is needed to inactivate 90% of the present viable population. Okay, so let's make this simple, right? Let's say that we are talking about 60 degrees Celsius. So again, the D time, or the decimal reduction time, would be the time that we would need at 60 degrees Celsius to reduce the number of microorganisms by 90%. So let's say that we have a can of beer, right? And then in that can, there's 1,000 microorganisms, right? So then the question is, how long do we have to treat that beer at 60 degrees Celsius for the number of microorganisms to go down from 1,000 to 100? That's a 90% reduction, or one log cycle, right? One logarithmic cycle, right? Okay, so that's the D value, right? So obviously, that is going to be, again, wrong button, different for different microorganisms that are going to be present in the beer. It's also going to be different for different types of beers, right? Because the composition is important, you know. What are the IBUs? What is the pH? Right? That all plays a role. And it's really telling us how sensitive different microorganisms might be at that temperature. And this is just a formula which explains what I've been talking about, right? Where D is the decimal reduction value, and dT is the temperature. So let's say 60 degrees Celsius, this would be 60. This T over here is really the time, right? And we have the initial concentration of microorganisms at time 0, and the final concentration after, you know, so many minutes. So let's say that, you know, we have some microorganisms or group of microorganisms that have this decimal reduction time at 60 degrees Celsius of 5 minutes. So again, what that means is that after 5 minutes at 60 degrees Celsius, the number of microorganisms is going to go down from 1,000 to 100. So that's what the D value is. So it's important to understand that. Okay. Just a sip. So in order for us to be able to talk about pasteurization units, we also need to talk about the thermal resistance constant, or the Z value. So now the Z value is really the increase in temperature which is required to reduce the D value by 90%. Okay, so let's go back to that example, right? So if at 60 degrees Celsius we needed 5 minutes for the number of microorganisms to go down from 1,000 to 100, the Z value is going to tell us at how much we need to increase the temperature in order for this to happen 10 times faster. So let's say that, you know, at 60, it takes 5 minutes to go from 1,000 to 100. How much do we need to increase the temperature for this to happen in 30 seconds or half a minute, right? So that is the Z value, right? How much do we need to increase the temperature for the D value to increase by 90% or decrease by 90%, right? So obviously, that is also going to be different for every single microorganism out there, or for a group of microorganisms that might be present in our can of beer, right? So when we're talking about pasteurization units, in the formula which we're currently using, this is the Z value that we're using. This is the Z value of 6.94 Celsius degrees. That's the proper way of talking about Z value, because it's the temperature difference. So it's not degrees Celsius, it's Celsius degrees, right? So, and sometimes we just, you know, round this up to 7, right? We need 7 minutes, you know, And you'll see this as part of the formula. So this is the formula for the Z value, where T0 and T1 are those two temperatures that I've just mentioned, right? Temperatures of two different D values, right? Okay. So this D value and Z value should really be determined for each microorganism, right, which is present in the beer, or a combination of microorganisms, to give us the overall D and Z value for the product, right? So obviously, in practice, this would take a long time, right? Nobody has the time to do this every time that you're pasteurizing and all that, right? So that's why we're using, a standard value of Z, which equals, 6.94, or, we round it up to 7. And all this is based on work by Del Vecchio and co-workers from 1951. So this is more than 70 years ago, right? And this is based on the work that they've done where they looked at, the data of different microorganisms which are commonly found in traditional beer. So beer that has 5% alcohol, right? Okay. So this is the data from that work, right? Okay, so let's have a closer look here, right? So we have, a graph here, and this is called the thermal death curve, right? So, then the students are asking me, well, it's not really a curve, it's a straight line, right? Well, the only reason that this is actually a straight line because this is the semi-log scale, right? So we have temperature here at the bottom, right? Celsius, degrees Fahrenheit. But over here on the y-axis, this is the log time in minutes, right? So that's why this is really not a curve, but it's a straight line, right? So what we can see here is that original work from 1951, what they found out with those typical microorganisms that are beer spoilers that you can find in a beer is that, if they pasteurize beer at 60 degrees Celsius, the D value there is 5.6 minutes, right? So this, above this line, or curve, if you will, this is the death zone, right, lethal zone. Anything below the curve, you still have microorganisms which are there and which are surviving that heat treatment, right? So they've done this at a bunch of different temperatures, right? So again, it's not just 60 degrees Celsius when we're talking about pasteurization. So, you can see that they've covered here a range between 50, let's say, and up to 70 degrees Celsius. So if you look closer, again, at this line, and if we look at these D values, you can see that one log cycle here is this Z value, right? The Z value of 12.5 degrees Fahrenheit, or 6.94 or 7 Celsius degrees, right? So if you go down from 60 to 53 degrees Celsius and go up where this hits this line, you can see that the D value there is not 5.6, but it's 56 minutes. Or if you go up from 60 degrees Celsius to 67 degrees Celsius, so again, one Z value, right? You'll see that this time which is required is really 0.56 minutes. So one log cycle, that's what the Z value is. And that's what we're using when we're calculating pasteurization units, that Z value. Okay. So a bunch of formulas here, but pretty much all that I've been talking about. This is the formula for lethality at a set temperature, right? So again, this temperature can be 60 degrees Celsius, but it can be below 60, it can be above 60. So how do we calculate pasteurizing units at the set temperature? Well, this is the formula that we're using. These are our pasteurization units. This is the time at that one temperature, right? And then we have 10 to the power of temperature, right, which can be 60 or 61 or 67, minus 60 divided by that Z value, and the Z value is this 6.94 or 7. When you read different books or different literature, you're also going to find this formula, which is exactly the same as the formula over here, because if you take 10 to the power of 1 over this Z, you get exactly 1.393, right? So exactly the same formula as 1 over here. But again, this is the formula to calculate PUs at the set temperature, right? So for example, if we're covering, let's say you have a tunnel pasteurizer and the bottles or cans go, travel through the tunnel pasteurizer, you have different zones. So you're going to start at very low temperature, you're going to warm them up, keep them at, let's say, your target temperature, which might be 60 degrees Celsius, and then cool them down. So if you want to calculate the entire, cumulative pasteurization units or total pasteurization units, you really need to use this formula, right? So this is the total pasteurization unit at any temperature profile. So pretty much you're calculating this for, each temperature. You don't really need to worry about temperatures below 50 degrees Celsius because the PU contribution is really minimal. So that's how you can calculate the PUs for any temperature profile, right? Whatever you're using, batch pasteurization, tunnel pasteurization, flash pasteurization, right? Okay. So again, looking at that lethal rate curve, all that this is showing you really, again, we have temperatures at the x-axis, Fahrenheit, Celsius over here, and then we have the PUs per minute, right? So obviously, if we're talking about 1 minute, at 60 degrees Celsius or 140 degrees Fahrenheit, right? So this would give you 1 pasteurization units. But if you're pasteurizing at 67 degrees Celsius over here, in 1 minute, you're going to get 10 pasteurization units. Or if you go down to, 53, you're really at 0.1 pasteurization units, right? So, okay. Okay, so this is just an example of a small batch pasteurization that we're doing at KPU as one of our labs in advanced packaging, right? So this is actually, students have produced this graph. So what we can see here is that, we're actually tracking PUs at temperatures over 50 degrees Celsius, hitting our target or slightly above 60 degrees Celsius, and then going down. So this line here is the beer temperature, right? So we have a thermometer which sits in the cold spot in a bottle. And what we're doing as we are warming it up and cooling it down, we are measuring the temperature and we're measuring the time. And then we're calculating the total pasteurization units. So you can see here that, over almost half an hour, as we've been warming the beer up and cooling it down, we got just over 10 PUs, less than 11, right? So this is, again, just an example of how you would, calculate the total pasteurization units or cumulative pasteurization unit during any heat treatment that you're going to, put your beer through. Okay, so then what are the options out there? So when we're talking about pasteurization, well, at KPU we first started playing with this. This is sort of a benchtop experiment. So we're using one of our small brew systems. This is actually our, mash/lauter tun. We fill it with bottles, and we're using a pump. We're keeping it on an induction heater, and we use a sparge arm. There's a thermometer sitting in one of those bottles in the cold spot, and the students are standing there recording the temperature and recording the time. And with those two values, they can actually calculate, how many PUs are they going to get for a specific heat treatment that they give to the beer. And we can hit our targets, very accurately. Then, for smaller producers, there's the option of batch pasteurization. So this is one small batch pasteurization. A lot of folks in the cider industry, small cideries, they all have to pasteurize their beer. Most of them are using batch pasteurization. And then, of course, there's the tunnel pasteurization and the flash pasteurization, right? So we're going to quickly look at those options, right? So with batch pasteurization, again, this is for a small production, but typically what they are is just a holding vessel, and you can have rack for beer or bottles or cans. There has to be a lid for safety reasons, because obviously, the bottles can burst, the cans can, pop. You're actually creating a lot of pressure inside a bottle of a beer or a can of a beer when you're warming it up, right? So those pressures, you can easily, hit 6 bars, which is, as much as a can withstand, or, like if you're going to higher temperatures, this can even be higher, right? 8, 10 bars, and so on. So obviously, the carbonation level is also going to be important there, and your target temperatures are going to be important there. Those things can be calculated if you use Henry's law and if you know Henry's constant for CO2 at different temperatures and so on, just for the safety, right? So then, you can have some spray nozzles. There's usually a water pump here, which is used to recirculate the water. This is a heater. And then, you can hook this up to a computer, and, you can just say, okay, I want to have like 15 PUs, and it will just do it for you, right? You don't really need to worry about anything. But again, this is a small unit, right? So for larger producers, probably the most widely used method is really a tunnel pasteurization, right? It's also the safest way to produce biologically stable products, simply because you are actually putting the product in a sealed container before you do a pasteurization, right? So those cans or bottles are traveling through your tunnel pasteurization. You have a target temperature. So you're going to keep it there for a specific period of time, depending on how many PUs you want to hit. Most of the time, in a tunnel pasteurization, we are targeting about 60 degrees Celsius, maybe 1 or 2 degrees Celsius higher than that. And then after that, you're cooling the beer down. And the time scale, again, depending on your unit and depending on how many PUs are you trying to hit, it can be like up to 1 hour. And this is typically what tunnel pasteurization looks like, right? You have several different zones, 7, 9, or so on. And what's happening here is that as the bottles or cans are going in, you start with heating. So you're spraying warm water over those cans or bottles, and that warm water is actually the water that you're pumping from your last cooling section over here, so you're recovering some heat. So that typically happens between section 1 and 7, and then 2 and 6, and so on. And then in the middle you have like the superheating zone. So this is where you're actually reaching your target temperatures, holding zone. So let's say you want to stay at 5 minutes at 60 degrees Celsius, and then another cooling zone, right? So the water that you're spraying is passing, through the containers and through the conveyor and collected, and it's being reused, right? So this is really done, obviously, to save energy. Another option is flash pasteurization, right? So this is really an inline heat treatment, and flash pasteurization unit is really a plate heat exchanger, same way like as your wort chiller, right? So again, this is designed to achieve certain stability, right? But this is before packaging, right? So the beer is pasteurized at a higher temperature, much faster, but before you package, right? So again, you need to hit this balance between inactivation of microorganisms, but also, the effect of heat on the sensory qualities or properties of your product. But this is a short heat treatment. Like we said, that the tunnel pasteurization, it could be up to 1 hour or so. This is happening really fast, but your target temperatures are also higher, right? So now we're talking about 70 or over 70 degrees Celsius, 72 or so on, right? So, and this is what the typical flash pasteurization would look like, right? So you have a plate heat exchanger. Typically, there's 3 zones inside the plate heat exchanger. There are units that have the 4th zone over here inside the plate heat exchanger, but, other option is to have this holding tube as the 4th zone. So what's really happening here is you have a cold beer, right, that can be around 1 degree Celsius, and going into the 2nd zone, which is the B zone over here. This is the regeneration section. So this cold beer that goes into the regeneration section is actually being warmed up by the hot beer which is coming out of the holding section, right? So we're recovering a lot of heat this way. You can actually recover 95% of the heat in the flash pasteurizer, right? So then this beer actually gets warmed up pretty close to your target temperature. So I'd say this is at 1, you can warm it up to about 65 degrees Celsius or so on. And then it goes into the heating zone. So you're just adding a little bit more heat over there. So you would use a heating medium. It could be water from an HLT. You hit your target temperature, let's say that this is 70 degrees Celsius, and then it travels through the holding zone, which is just, like pipes, a series of pipes. Can be different profiles. And this depends, how many PUs are you going to get actually depends on, how fast you're pumping your beer through this holding section, right? Because you know, the faster the flow rate, the lower, the less the time that it spends in the holding section. So that beer goes back into the regeneration section, so we're recovering the heat. So now this beer is being cooled down by this incoming cold beer, and then it goes into the last section, which is the cooling section, so we can use, you know, cooling medium, glycol, something like that, and then cool the beer down all the way to 1 degree Celsius. But again, this is happening before the beer is packaged, right? So then it goes to the packaging line from here. Okay, so now if we compare those two, right? So the tunnel pasteurizer, the flash pasteurizer, the first obvious thing is very different in size, you know, the floor area requirements and so on. So here beer is, again, inside a sealed container. You're spraying hot water on top of the beer. Over here, we have a plate heat exchanger, counter current flow, you know, higher temperature. So the beer needs to be packaged after that. So there's the rest of the operation requires a sterile operation. And if you look at the timeline, again, you know, this takes, you know, like up to 1 hour or so. The flash pasteurization, this is happening really fast, right? But the target temperature here is 60 degrees Celsius. The target here is 70 or higher than 70 degrees Celsius. So this happens in just a few minutes. Okay, so again, if we compare those two, right, we can definitely say, you know, like tunnel pasteurization, the most reliable, no risk of reinfection. Again, sealed product, right? High capital cost and installation, higher operation cost. Larger floor area is required. This is more simple, lower cost, you know, smaller foot area, but the system needs to be sterile. Then there's also a challenge of, you know, like your filler operation, start, stop, and so on. You have to deal with this, right? So you have to have some sort of a buffer vessel, where all that pasteurized beer from a flash pasteurizer needs to go. Okay, how are we doing for time here? Okay, we're good, I guess. All right, so now I'm going to tell you a little bit about you know, a few things that we've done at KPU when it comes to non-alcohol beer. So really, not all that much. We've done only 2 batches. You know, the first batch was actually done last fall as part of our Brewing 3 course. So it was the second-year students that made the beer, and then we've done it in this year in the spring with our first-year students as part of the Brewing 2 course. So, you know, when we came from MBAA last October, there were some sessions on non-alcohol beer. We've tried some beers over there, and we were not thrilled about those. And then we said, okay, well, let's try this at KPU. Let's see what we can do. And we've decided to actually make a stout. So that first stout that we made after we came back from the conference, right? After we've you know, made a beer, we've pasteurized it, we've tried it, and we were sort of pleasantly surprised, to be honest. It was our first try, right? We didn't find really any off flavors or anything like that, and then we've decided, you know what, let's send this to a competition. We've sent it to a national competition because we wanted to get the feedback from the judges. You know, we might be biased, you know, it's our beer. And actually, you know, the beer did not win any awards, but we did get the positive feedback from the judges. So we were happy about that, and then we said, you know, like, we're going to tweak a few things and then try it again, you know, like as part of our other course. So we've tried it in the spring with first-year students this time, and we produced a beer which did win a medal, silver, at the US Open College competition. Of course, much smaller competition than the national competition. But, you know, like, we're really, really happy with it. And then, you know, we've decided to keep going. You know, we didn't really want to stop there. So after we won that award, and, oh, geez, this is, you know, some of the slides have changed, but that's fine. You know, then I've decided, okay, I'm going to sit down and actually make a food safety plan, because obviously for non-alcohol beer, you know, you have to have a separate license, so you have to talk to your health authority. So I've submitted this food safety plan, which is sort of like a HACCP plan, and that got approved. So now, you know, we can actually make non-alcohol beer, and we can try to sell it, because the 2 batches that we made, we've destroyed, right? It was just, you know, for you know, to teach our students, let them play with it, and you know, just to see what we can do, what we can And then after that, we've said, if we are really going to make some non-alcohol beer, that 40-liter pot that I've showed you as our benchtop pasteurization unit is not going to cut it. So if we want to pasteurize an entire batch, how are we going to do it? And then we said, okay, we have a large sink, right? So let's use that sink as a batch pasteurizer. So we can put 200 cans in a sink. And so the way that we're doing this is we're using a dedicated CIP tank, which we can use to warm the water up, and 2 CIP pumps, right? So we're making a circle, we're recirculating everything, kind of what you're doing in a batch pasteurizer. The temperature profile is actually similar to what you would get in a tunnel pasteurizer. And we've done one trial, and we were able to hit our PU targets on that first trial. And our target for non-alcohol beer was 120 PUs, so that's a lot. So it took us like an hour and a half to do that in this setup. Again, the important thing here, safety. So we have a plexiglass cover, but we were, and our target temperature there was 65 degrees Celsius. Now, the stuff that we've pasteurized was just some old beer, some old cans that we've had, so it was not non-alcohol beer. So a whole bunch of different cans that students were making. Some of those beers were their signature products. And we knew that a lot of those cans are going to burst. Because again, I just quickly did the calculation, and I knew that we are going to get a pressure of up to 8 bars. So yeah, we had a lot of cans that were popping, but interestingly, the cans that were bursting were cans that were overfilled, mostly beer, which is like a Hefeweizen, which is highly carbonated, and of course there's the yeast inside the can, right? Most of the cans actually did not burst, which was interesting because I expected way more of those cans to burst. So after we've done this pasteurization trial, then the question is now, what is the PU level, right? If we're talking about non-alcohol beer, right? So what should be the target? That's $1 million question, right? So then there was another thing. So when we were brewing this beer, we actually applied for a grant. So SRIG is the Student Research and Innovation Grant, and we got the grant. So we had 3 groups of our students that actually did a little research project. First-year students as part of this brewing too. So one group actually looked at the carbohydrate profile of the beer, which was mashed at different temperatures, right? So we had one control, which was done at 68, and then temperatures higher than that. So we looked at the carbohydrate profile. The other group, looked at pasteurization levels, or how they can hit, a range of different pasteurization units, so from 80 to 120, even up to 150. And then the last group was doing some micro work on that pasteurized beer. Okay, so I'm going to show you some of that data. So again, this is all students who did this and produced these graphs and all. So first of all, the first group was looking at the carbohydrate profile. So what we can see over here is the sugar profile at several different temperatures. So the control was done at 68 degrees Celsius, and then we had 72, 73.5, 75.5, and 80. And what we can see is obviously if you're mashing in, hot, as you're increasing the temperature, you get lower sugar concentration, right? So specifically, the levels of fermentable sugars are dropping down because, you're deactivating, obviously, beta amylase, and alpha amylase works really slowly. So the conclusion there was that really, if we get to 74 degrees Celsius and higher, the sugar profile does not change all that much, which was expected. And then also, they were taking samples from the fermentation, and they did it at the start of fermentation, 12 hours, 24, 48, and then final package. And this just, confirmed that the yeast that we were using is really a maltose negative yeast, because that yeast only utilized glucose and fructose. The levels of maltotriose and maltose were not changed. And then this is the alcohol, right? So also confirming that, you know, we have less than 0.5% alcohol in that beer, okay? And then the third group, the second group did a study on pasteurization units. So they, you know, produced 4 different schedules in order to hit 80 PUs, 100 PUs, 120, and 150. And this just shows, you know, that those graphs that I talked about, you know, like the temperature in the cold spot and the PU accumulation, right? So we've confirmed that, you know, we can hit our targets. And then the last group did some micro. And what we can say about this is that the data was really inconclusive. You can see here that, you know, they looked at beer, and they also had controls, but they even had some, you know, colony forming units in the controls. So, you know, obviously, you know, the contamination went down, but we have concluded that because of the, you know, the sampling and plating techniques, after all, these are first-year students just taking micro, right? We cannot make any conclusions, you know, when it comes to PU and the level of contamination. Okay, so what should be the targets for non-alcohol beer? Well, there's not all that much out there, really. We have the EBC guidelines for low alcohol beer that are, you know, asking for a target between 60 and 80 PUs. Then, if we're talking about non-alcohol beer, the typical targets would be 80 to 120 PUs. So this is the data from more than 30 years ago. What's unclear is really how they actually calculated those PUs, and it looks like that they were using spore formers and worst case scenario, right, when it comes to, you know, what should be the targets. And now there's, you know, obviously a lot of research happening. And so the last issue of the MBA Technical Quarterly talks about pasteurization, talks about non-alcohol and low alcohol beer. So I just want to show you, for example, some data from this one paper from England. So they used a bioindicator in order to determine what should be the level of pasteurization. And so they looked at a whole bunch of different non-alcohol beers, right? And those, so obviously less than 0.5% alcohol. And those beers had very different, IBUs and the pH, but the IBUs were the biggest difference, right? So what they found is that, you know, like in the beer that has very low IBUs, non-alcohol beers, what they required was 130 pasteurization units, right? But what's also really, really important that this bioindicator that they used, they've determined that the D value for that particular microorganism in this beer with low IBUs, you know, the D value was 21, almost 22 minutes, okay? Now that same bioindicator, the same microorganism, in a different non-alcohol beer, which had 50 IBUs, you know, they said that they've only needed 30 pasteurization units, but the D value, you know, is of course much, much lower here. So, you know, obviously IBUs play a big role. I mean, this is not, you know, a straight answer. Okay, we just need to look at IBUs and based on that determine how many PUs we need, right? This is not a linear regression thing. This is more like a analysis of variance. There's many different things that are important here. But one of the main factors, you know, in this work seems to be the level of bitterness, right? So again, this bioindicator that they've used, it was actually ascospores of Saccharomyces cerevisiae, I don't remember, like something like BRYC501, right? So they have identified that microorganism as a really heat-resistant microorganism. So they've also decided that, you know, like they have inoculated those different beers with 1 million cells of this bioindicator. And they said that, you know, successful pasteurization would require a log reduction of 6, okay? They've also used other microorganisms some viable bacteria, which are in the food science are typically used as pathogen surrogates. And the same bottles were also inoculated with 100 million cells of the bacteria, right? The viable bacteria, so not spores. So, so the successful pasteurization would require a 6-log reduction in the bioindicator and complete destruction of all the viable bacteria that they've used in inoculation, right? And again, those are the conclusions, right? So how many PUs these different beers have required, right? And actually, like if you determine the D value of the microorganism or a group of microorganisms, the way that, like you can see here, the way that you can calculate your IBUs is you just multiply the D value by the number of log cycles that you have the reduction. So if you look at here, like 22 times 6, or almost 5 times 6, and you get to these levels of PUs. So, like non-alcohol beer, obviously with lower IBUs is going to require much higher pasteurization units. So IBUs are important. The pH value is also probably the second most important thing, like if we remove alcohol. Okay, so what can we say about all this? Well, first of all, obviously, in order for us to be able to determine, how many PUs do we need to know, to get the stable product. It will depend on the beer style. It will depend on the contamination, meaning which microorganisms do we actually have present in the beer, what's the type and the number of microorganisms. And then the target is always going to represent, some sort of compromise between, a minimal theoretical value and some higher empirical value, right? There's always has to be some safety margins in your, PU units, because there's going to be, some variations with the beer, with the process, and so on. So currently, there's a very wide diversity in opinions, and those opinions are different between different breweries. They're different between different parts of the world. But however you decide to determine, what should be my PU levels, this should always be based on some scientific principles, right? There's 3 different ways that the brewers are looking at this. When they're deciding. Most of the time, unfortunately, it's trial and error, right? So we're basing that decision on some previous experience, and we really have no experience when it comes to non-alcohol beer. So it's, if you ask me, it's like playing a Russian roulette, really. The other option is to take sort of the endpoint approach, and which is really like the work from 9051. You need to look at different temperatures and what is the thermal death time at different temperatures for different microorganisms. And then you can also think about specifications, right? So what should be our specifications for different beers, right? So when it comes to, products before pasteurization, not a lot of breweries are publishing that data, but, generally speaking, I think, we can say, less than 10 colony-forming units per milliliter, right? And if you think about the final product after pasteurization, we probably, the specifications should be, 10 to the negative 6 per a can of beer, which is like if you have 355 mil. Now, if you convert that into milliliters, it's 2.8 something times 10 to the negative 9. So if you now think about, okay, if we start from less than 10 and go down to, 2 point something times 10 to the negative 9, that's 9.5 log cycle reduction, right? So maybe that's how we can think about these things. But maybe you don't have 10 colony-forming units. Maybe you have, 1 or 0.1 or 0.01, right? So it all depends on what are the typical microorganisms, contaminants in your operation, in your brewery. I think what the industry really urgently needs is discussion and, some sort of consensus when it comes to non-alcohol beer. How do we get there? That's a tough one. Probably one of the best things would be for some of the organizations in the industry like MBAA, ASBC, Brewers associations to form some sort of committee. They've had emerging issues committees in the past, or maybe work together to give us some guidelines and to give us more specific answers, other than, oh, it should be between 80 and 120. Because if we're talking about 80 to 120, what are we actually talking about? Z of 7? I don't think so. It could be something completely different from that. So then when we're saying, oh, we're having, we have 120 pasteurization units, well, that's kind of risky because that Z value might be very different from 7. So lots of questions or lots of answers to be answered, right? That's all I have for you, really. Now we can maybe start a discussion about this thing. So how many of you, let's say, how many people are actually producing currently non-alcohol beer here? 1, 2, okay. I know what you're doing. Up there was a hand. How are you treating your? Not pasteurized. Okay. Yeah. So, yeah, that's where we are. Yes. I'm afraid I don't have any definite answers.
I'm really curious about the preservative aspect, since pasteurization is such a barrier to entry for 90% of the breweries at this conference.
Yeah.
I don't see a lot of talk about it, though, like the sorbate benzoates. So many foods we accept on a daily basis do use food preservatives.
Yeah, yeah. There's definitely that option. Personally, it's the question about which preservatives can be used, right? I know that some local producers are using preservatives in their non-alcohol beer. I have to admit I'm not an expert on preservatives. I deal more with the pasteurization and so on. But there's definitely products that are there, and there are new products that are coming. I would recommend anybody who's really interested in this subject to get a copy of the last Technical Quarterly. There's one paper that talks about those different types of preservatives, and they're talking about I think like white mushroom cytosan fibers that can be used as preservatives. So there's lots of research currently, and there are actually commercial products from that are available out there. Again, unfortunately, I'm not an expert in that area. Yeah. Yes.
In terms of ingredients, non-alcohol beers tends to be watery, lacking body. Have you looked at adding ingredients to increase the body mouthfeel?
Yeah, yeah. So that was, for example, the beer that we've produced. That was one of the obvious things, is that the body was lower than what we wanted it. So I mean, you can look at your mashing profiles. You can change your the malt that you're using. And then you can also use different things that can add body and maybe add some other flavors that are there. But like if we're talking about sensory of non-alcohol beer, it's really a separate category almost. So they should not be judged as regular beers. There are non-alcohol beers that are going to have their own flavor characteristics that are always going to be there. We can try to produce beers that we want to be as close as possible to beers with alcohol. But again, I'm talking about the biological methods. If you're using reverse osmosis, that's a different story. You're removing water and alcohol and then adding back deaerated water, so you're closer to the original flavor, I would say. Yeah.
Filtration just not get you there, or in place of pasteurization?
It's an option, but again, you need you need to look at exactly what you're getting, and I would say maybe in my mind, sterile filtration, depending on the type of beer, but you can maybe use in combination with much lower pasteurization, right? So if you reduce the micro load on your unpasteurized beer, then, you know, like you don't really need to be talking about 80 to 120 PUs, but you can drop that down much lower. I'm not sure if anybody, probably some companies might be using just sterile filtration, but I'm not certain. Yeah. Yes. Okay, yeah, all right. What's?
You had on there low alcohol and non-alcohol beer.
Yeah.
What defines low alcohol?
Again, if we look at, you know, like the legal definitions, they're very different, right? But low alcohol, I would say, would be, you know, 2 and below. And then if we're talking about non-alcohol beer, again, legally, when it comes to labeling in Canada, you know, it's actually 0.05, but it's like you can buy a non-alcohol beer of less than 0.5, right? So that would typically be, yeah. Yes.
Like a combination of various things like chemical pasteurization, filtration, and heat pasteurization.
Yeah. So that's what, like the previous question was about sterile filtration, and what I've said is that maybe you can use the combination of those two, you know, run it through a sterile filter, and then you can drop your PUs to much, much lower levels. I don't think that people are using actually a combination of different, you know, chemicals and pasteurization. It's typically either or. You know, it's always, you know, the big question, of course, for the smaller brewers is, well, how are we going to pasteurize our beer, right? So again, there are some producers now that are offering much smaller pasteurization units, you know, smaller flash pasteurization. But again, with flash pasteurization, you really have to have good control of everything that's happening after that. So, yeah. Any other questions or comments?
Great presentation.
Thank you. Thank you. All right, thanks. Okay, I think we have a break now.